So I promised last week, okay, that we would continue with how do we know that the earth moves, okay? Because I know when I'm driving my car, I know I'm moving because it's doing all kinds of vibrations and noises, and okay? But if I stop, I don't feel anything. I hear the systems, but how do we know this place that we live on, okay, is actually moving? So, and that's one of the questions that when I was in elementary school, I'd asked one of my teachers, I forget if it was 5th grade or 6th grade, and she said that the earth moves around the sun. And I was pretty pain-bashed in those days. So, and I said, well, how do we know that? Wow, it's here in the book. See, the sun's in the middle, and well, we go back, not even that long, just about 1,000 years. Most of the people on the earth thought the earth did not move, and that everything moved around us. Okay, and even some of the scholars by then, it took a long time for them to accept the evidence and that's what we're going to talk a little bit about tonight. We're going to talk about the evidence, the proof that the earth does move. All right.
Excuse me, and I have a question from last week. Maybe I missed it, but you talked about the planets having an elliptical orbit.
Yes.
Why is it elliptical and not circular?
Well, that was explained. Johann Kepler discovered that. He discovered that was the path that they followed, and but he didn't know why exactly. Okay.
Do we know why though?
Okay. Well, we do now. Okay. So at Kepler's time, okay, at the beginning of the 1600s. We had to wait almost another 60 years for Isaac Newton to come along and explain why planets behave the way they do. But Kepler and Copernicus and others had a pretty good idea of the physical path, not why it follows that path. And we had to wait for Isaac Newton to come along to explain. Okay.
So that's the second.
Yeah, that's what we're going to see tonight.
Okay.
So when we left off, one of the things that I forgot to mention is that at the time of Kepler, on the beginning of the 17th century, 1600 or something, there was a gentleman in Italy by the name of Galileo Galilei, right? And here's another failed student, okay? Kepler was failed because he wanted to become a minister, but he never finished his ministry. He went to get a job, okay, because he was good at math, and they were looking for math teachers. The rich people were looking for math teachers to teach their kids, all right? So he gave up his vocation, I guess you'd call it, and started teaching math schools. I guess he was a terrible teacher because he'd be talking, and he had like, and he got paid according to how many students each of the parents would pay him, okay, for it. So if he had 40 students, he was very rich. But not too long, after a few years, he was down to just a handful of students because he would talk to the board. Okay, and he was describing stuff that he was kind of trying to discover where they went. So he wasn't. He was very bright and he knew the math pretty well, but he had a hard time communicating with the students. So, but what he did when he finally went to visit Tycho Brahe, the guy with the missing nose. So at first he had a silver nose made, but then when he got rich, when he became the king's astronomer, which meant he cast a horoscope for the king, okay, he had enough money to have his nose redone, and it was a golden nose, okay, that he had. So if you look carefully at pictures of Tycho Brahe, you'll notice there's a little shiny glint in there. So what Tycho did, and which is what other astronomers before him did, is he kept track of all his observations. So on any given night, let's say he followed Mars, he had, they used to use sextants and try to, there was a little weight hanging down and gave you how many degrees up it was, and then he figured out what the longitude was, the altitude, longitude, and but it was kind of blurry, so he made himself a sextant as big as this room. Can you imagine that? Okay, a sextant is just like a semicircle, and he was able to get positions, okay, extremely accurate, the best of his time, and he recorded that all night long. Okay, well, he didn't have to work, all right, and he had a family of girls that kept track of he had a family that took care of making sure the poor people that ran the island or that farmed on the island, he had to get his 10% of their crop. Okay, so and during the day he slept or he entertained people. All right, but when like I told you about his episode, he had the bladder infection and as he died slowly because it took several months before he passed away. And he didn't want all that. He had 40 years of observations in books in his library. He didn't want that to be wasted. So he got in contact. He had an apprentice. John Kepler came to see him because Kepler wanted to get some money too and support his family. So, and he told Kepler, okay, in confidence, I don't let all this, see if you can figure out something from that, which he did. Well, his family didn't want to give up the books, but one night at midnight he loaded up his wagon and his kids and took off. Okay, went back, he left the island. And so he was able to carefully trace it. The first thing he did was find the orbit of the Earth. Now, the orbit of the Earth around the sun, okay, he did that by checking the size. You know, when something is closer to you, you look bigger, right? And when you're further away, so just by checking to see the size of the sun, okay, and the observations, he was able to tell how far we were from the sun. Okay, so he worked his way backwards to that. So he came up in an orbit that was, at the time, there was sometimes during the year that we were closer, other times that we were further, but he still thought that the orbit was a circle. So he thought it was a circle slightly moved over. All right? And then from there he said, well, maybe I can find the orbit of Mars now. And it's when he got Mars, which had a 7% eccentricity, that he noticed, and then he started checking it out, and he found the major axis in the center, and then he said, this is an ellipse. Didn't know why it was an ellipse. And then he started doing the paths of the other planets after that, and they were also elliptical. Okay, now why they're ellipse or why they go faster when they get closer, he couldn't answer that. Isaac Newton came along and made the discovery. So I'll get to that in just a second. Why did a fellow like Galileo, okay, he almost got burned at the stake, by the way, Galileo, because he proposed, he read Copernicus' stuff, he read Kepler's stuff, and he, okay, said, hey, boys, that makes more sense than the old, what Ptolemy and the old guys say. But then he was misfortunate. He heard the story about a guy in Holland, okay, the Netherlands, that had been able to look at faraway objects and see them closer by using two lenses. And what he would do is he'd hold one lens next to his eye and then the other lens out. And I have a bag of lenses. I should have brought them. We could have done that. But if you have two magnifying glasses, you can do that yourself. Okay, put one next to your eye, which would be the eyepiece, and then the other one is the objective. And then you move the other one until. So what happens is the lens collects the light and makes it come to a point. Okay, you play with magnifying glass, right? See the sun coming to you can make an ant burn or whatever. No, not an ant. You can start a leaf burning or something. Okay. And the magnifying glass is what Lavoisier had used to light the candle inside of the sealed dome and all that stuff. So what it does is it forms a little image, okay, of what the light that's coming from, and then the other magnifying glass, when you move it, it actually enlarges that image, okay. Now the fact that the first lens is this big, let's say, okay, it collects the light coming from an object that's this big and brings it down. So what happens to the intensity of that light if it gets focused like that? It gets pretty bright, doesn't it? So that's the secret of the telescope. Its first objective is to make dim objects, especially objects that are far away and not much light comes in. First objective is to make that object brighter and clearer, not bigger. The second lens is the one that makes it bigger. Okay, and so in telescopes you can choose how big the second lens is, how big you want the image. The more you want it magnified, the more blurry it is. Okay, and it narrows it down to just a small section. So I tend to use eyepieces that have a short, not a short, but a fairly long wavelength, focal point. Okay. So can you imagine how do we see stuff? Well, the light has to enter our eye, doesn't it? Well, how does it? There's just a little itsy bitsy hole there, okay? Around the little hole, the pupil. So what if you could make your pupil bigger so more light would come in? Well, that's what happens when you go in a dark room. Okay, Mother Nature made that iris to expand so more light comes in. The problem with that is that as it gets in, the lens in your eye is thick in the middle and small on the end, which is, let's see if I have mine. Where did I put it? Oh, I have it. Okay, so here's a lens, all right, and the light coming in. All right, if it comes from far away, the rays are pretty much like this. Now, this side part of the lens here, that looks a little bit like what? A triangle, right? What's another name for a piece of glass that's in the shape of a triangle? A prism. So what happened is when light goes through a prism is that it refracts, it changes direction. And different colors refract differently. The one that refracts the most, okay, is the blue. All right, so if you just look at, forget the rest here, just look at light through a prism, all right, this would be blue. But one that refracts the least is the red. Okay, then you have orange, yellow, blue, indigo. It's actually the violet that refracts the most. We don't see violet very well, okay? We see blue better than the others. So when that happens, okay, you get a fuzzy image because some of the colors are here and there, all right? And from this side, you get the same thing except it refracts the other way, okay? So you get a blurry image, all right? So that's the type of thing that you get when you use the whole lens. So most people in telescopes, or in cameras, okay, they put a diaphragm here to let only the light go through the middle of it, okay, which cleans up the image quite a bit, okay. There's not as much fuzziness, all right. So, and that's why, by the way, not too long, well, a few years after Galileo died, Newton came up with a different type of telescope that made the light focus without fuzzing up. So instead of going through a lens and coming to a point, he had the light go through a mirror. Okay, so here's a mirror, a shaving mirror, or whatever, makeup mirror, okay, where the middle of it is curved in. Okay, so when light in a mirror comes in, it reflects. It doesn't go through, and it reflects back this way. Okay, what if the light comes in here? Well, it reflects back like this. So it's going in this part. If it hits right in the middle, it bounces right back. So this would be right in the middle, and it bounces right back. Okay, because it's flat there. So that too forms, that kind of a mirror forms an image. But it doesn't have to go through glass, so the image is much clearer. And that's why Newton, okay, liked that process. So instead of a refracting telescope, this is a reflecting telescope. Okay, the only problem is if you put your head here to look at that, what happens? You block out the light. So what Newton did is he was pretty ingenious. He put where it was almost in, he put another little mirror in here at 45 degrees, okay? And that makes the light come out here. So on a reflecting telescope, you don't look at it from the back, you look at it from the side, okay? So light comes in, goes through the reflecting, comes to a point, and there's a mirror that directs it out to you. So you stand sideways and your object's over there. All right. There's still a little bit of interference, but they make that mirror pretty small, that little 45-degree mirror. All right. So Galileo used he took that idea and he improved on it quite a bit. What he did is he made a housing. He used a piece of pipe for the first mirror and another piece of pipe for the second mirror so that he could focus. So it was like a big pipe and a smaller pipe inside, so you could slide them. Okay, so depending on how far, if your object is far away, like Judy, you have to do, but if it's closer, okay, then you have to adjust, all right? And it keeps outside light. It don't lets you look at what's ahead of you. So he improved on it. He didn't invent it. But I tell you, all right, he collected a lot of money because in Italy, he wasn't in the Netherlands. He got this idea by reading a book. Okay, he improved the telescope, and he was able to sell it, make a lot of money. Okay, he got the patent on it. All right, the guy up in Holland didn't know what was going on. So, and guess who he sold it to? The richest people in Florence, where he was living, sea captains. Why would a sea captain want a telescope? Do they study the stars? No, they study pirates. Okay, so they ended up building on their big mast. They end up putting a little nest up there for one of the sailors would go up with a telescope and look on the horizon all day long. Okay, if they could see a pirate, ooh, okay, they went the other way. All right. Because that was the biggest threat to shipping in those days were the pirates. And the storms too, once in a while. A storm would get your ship. So he made his money that way. And so he was able to he didn't have to teach anymore. He was a teacher. And I told you he failed. Well, what was his first vocation? Does anybody know? He wasn't a math teacher. He wanted to be a doctor. Okay? So there was a place where they were teaching anatomy, all right, at the school that he went. And it's a round building, okay, and in the middle of it, there's a big slab of stone. Then you go away and there's a set of steps. You go further, another step higher, so that it's like a round auditorium with steps. So the students would climb up, going up a stairways, and they'd stand around. Okay, you could have like, I don't know, 40, 50 students all looking in, and guess what they had down there? A dead person, okay. And so the teacher would come in, the professor would come in and say, okay, let's see where the heart is. First class, Galileo was up on the top tier, okay, freshman student. He looked at that, and, he couldn't stand the sight of blood. It made him pass out. Luckily, his friends grabbed him and said, hey, they brought him down. So he quit college for a while and he decided to go back. He had to settle for math. But he was a very good math teacher. So that's another thing I want to bring up. Okay, the people that made a lot of these discoveries, the early people, and still today, they didn't just discover and keep it to themselves. They actually took measurements and recorded them. And whenever you make a measurement, you need a number to tell you how big the measurement is. Okay, so they use numbers a lot. So someone who is mathematically inclined understood what to do with the numbers. Okay, it's called raw data. And so Galileo was a numbers guy. Copernicus was a numbers guy. Okay, Tycho, not so much. That's why he passed it on. All right. But if you go back to antiquity, guys like Ptolemy, he was a very good geometer, and he's the one that came up with the explanation of having a little circle going around a big circle, which explained the motion of the planets. Okay. So, and of course, the one that followed Galileo, the big name, is Newton, and Newton was so good at math, okay, that he actually had to invent a form of mathematics called calculus in order to explain this great big idea that he had about how the universe worked, okay. When he was 22 years old, well, actually he was like, when he was 20 years old, he was going to Cambridge University. He was a kind of an orphan. His mom was still alive, but his dad was a kind of a, he had a farm, but he wasn't too interested in farming, so his wife did most of controlling. And in those days, if you were in a farm, today you might as well have been a millionaire. Okay, why? Because the farm allowed you to grow crops, and there was a lot of hungry people around. People that were willing to come in and work for you for free as long as you could give them, okay, 3 good meals a day and a place to sleep. Okay, indentured people, or not indentured necessarily, but so that, okay, so Isaac was brought up by his mom, and he was kind of bright, so she sent him to Cambridge University. I think he was only 14 or 15, but by the time he got to be, he was almost finished his studies, there was a bad plague that went through London called the Black Death, okay? And it wasn't just in London, but it was quite a bit all over Europe. And this is a kind of disease where when you get the bugs inside of you, it kind of destroys your circulatory system, so your veins fall apart, so you have a lot of internal bleeding all over the place, so you turn black, you know, like when you have a bruise. So his mom said, "You're not going back to school, okay, you're going to stay home." And he was a spoiled brat, right? So he stayed in bed almost all day. He'd get up around 11, 12 o'clock, okay. His mom had plenty of servants to do all the work. So sometimes he'd go out for a walk, okay, throw pebbles in the pond, and he'd watch. If he threw 2 pebbles and met 2 sets of waves that would overlap, and he'd watch what they're doing, okay, stuff like that. One morning he wakes up, it was kind of late, and his mom had closed the curtains because she didn't want the sun to come in and wake him up. The moth had made a little hole in the curtain, and there was this little beam of light coming in across the bedroom, and there was a little bit of dust in there, so you could see that. So he grabs his glasses, is on the way over to bring the glasses, and he goes into the ray, and he sees on the wall different colors, okay? So the sunlight had gone through the edge of the glasses and spread out. Oh, okay. He'd never noticed that before. Nobody had ever noticed that before. So he went and he got a big lens and you know, like we did over there. And so he made all kinds of discoveries. Then he said, "Oh, I wonder what happens if you put a second lens." So when the light had gone through the prism, the white light had gone through the prism and spread out, if you put another prism here, it refracted back in and became white light again. All kinds of stuff like that he played around with. But one of the things he's most famous for, okay, is sitting under an apple tree late in the afternoon, okay, and as he was sitting there, okay, the sun was setting on one side, and there's an apple that fell on the side, right? You heard that story? And he turns over, and on that, the sun's over here setting on that, is a brand new, big new moon, right? Not new moon, but full moon. And he looks up and he sees these apples, and the branches are just bending from the weight of the apples. And then the light comes on. He says, if the Earth's gravity or whatever, okay, is pulling on these apples to make them come down, why can't it be pulling on the moon and pulling on it and make it come down? Okay? And he says, well, if it does that, maybe that's why. Because by then, he understood this laziness of matter called inertia, that if something is moving, it wants to keep moving. It doesn't want to stop unless a force pushes on it. And if it's going across in a straight line, it'll go change direction only if something pulls sideways to it. So people have tried to come up to explain why the moon went around the Earth. René Descartes thought it was because of the Earth's magnetic field that went out there, and there was iron on the moon and pulled it in, because they knew that magnets could pull on iron. So maybe that's what kept the moon going around. And Newton said, why can't it be gravity? Okay, but that was sacrilegious, because gravity, okay, supposedly only applies to Earth objects, things on the Earth. The objects up there, they're special. They're godlike, okay? So if we go back to Greek studies, they had figured out that there were 4 elements on the Earth. Everything was made up of 4 elements. The first one was earth. Guess what the second one was? Water. The third one, air. Fourth one, fire. Those 4 elements, okay? So for example, you take a pot of water, and put it on, as the fire goes up and gets into the water, all right, then the water, which is more dense than air, but because the fire comes into it, it wants to rise up in the air. Okay, so that's what they explain how steam was formed. All right, and people we're made up of the 4 elements. We have some fire, earth, water, and air inside of us. Different. So that's how they thought the world was made up of those 4 elements. There was a 5th element, okay, called the quintessence. Quintuplets, 5. The quintessence, the 4th element, was the heavenly bodies. And those had a completely different set of rules than the Earth. So in other words, those things were beyond the effect of gravity. Gravity didn't affect them because it was special. All right? So Newton had to think here, if gravity doesn't go up there, he says that's hogwash. Let's come up with a real force. So he said gravity goes up there. And then it would also explain why the sun keeps the planets going around itself too, because the sun is matter, okay? Well, not everybody believed that either. They thought the sun was some kind of a god, okay, burning and lighting up the world. So after that observation, he was able to explain the orbit of the planets being kept in orbit, because if the sun were to disappear, the Earth wouldn't go in a circle anymore or in an ellipse. It would go in a straight line. Okay, same thing with the moon. If we disappeared, our moon would go off somewhere. All right. So, but how does that work? All right. How exactly does the gravity get up there? So he started, okay, at the age of 20, coming up with a relationship. He says, well, the Earth is quite big. The Earth has a lot of matter, okay? And it also has a lot of inertia, resistance to change in motion. And so if the Earth has that property, it pulls on things depending on how much mass they have. So a small object, okay, gets pulled harder than a smaller object. Now, Galileo had found out that even though the big object gets pulled harder, when it falls at the same rate as the little object. Okay, how come? Well, here's part of the thing that Isaac Newton added to the picture. All right, so he says if I have a large object, okay, it's going to have a big force of gravity. Force of gravity. All right. If I have a smaller object, it's not going to have, let's say this is 10 times bigger than that one. So it's going to have 1/10 the force of gravity. I'll put little f here. Okay. So, but they fall at the same rate. Galileo, okay, had explained to us that the more mass an object has, the more lazy it is. So this thing accelerates. So he knew that an acceleration, I'll use A here for accelerates, depends on two things. So if I push on this empty bottle here, okay, I give it a little tap, it goes. Now if I take it, no, I won't throw it. But I take one that's got more mass, okay, and I push the same, it's not going to go like that, is it? Okay, I'd have to push harder to get it to speed up. Think of if you're driving let's say you're driving a Volkswagen, all right, and there's a little tiny 50 horsepower engine in the back, and then you jump into a Subaru, no, I mean a Chevy S10, okay, which weighs probably 10 times more. Instead of a 50 horsepower motor, there's a 500 horsepower motor, okay, that pushes even harder. And then you could race the Volkswagen against the, and probably the Volkswagen might win anyway, I don't know. But so the more mass you have, okay, acceleration depends on how much force, okay, but inversely on the amount of inertia or mass, okay. So something that has more matter is harder to get to move, and it's proportional. So he proposed that. So he said, okay, so big force, okay, of gravity, big mass. Now, let's look over here. We have this guy with a little bitsy force, but also has a little bitsy mass, okay? Let's say this force is 10 times bigger than that, and this mass is 10 times bigger than that. Guess what? What's 10 divided by 10? Still 1. Still proportionately the same. Okay? So that's how Isaac Newton, when he came along, Matt teach, okay, he was able to show that why the acceleration is the same for falling objects of different masses. Okay? Because not only do they have more force acting on them, they have more laziness or more inertia. It's directly proportional. Okay? So that's one of the things that he did. But he, trying to come up with an equation for the Earth, he had to work on the moon. He wanted to work on the moon. He says, if this is true, if gravity does go out all the way to the moon, all right, then by the time it gets up there, it's going to be quite a bit weaker. Okay, we know, for example, that the satellites that go around us, all right, the reason that they don't crash into the Earth or go flying away is because there's a nice balance there. As the satellite orbits the Earth, they make it go exactly 17,576 miles an hour, or some exact number, at that height. Now, if they move the satellite further up, it has to go a little bit slower because gravity is a little weaker up there. Now, how many of you have dish TV, a satellite, okay? How come that satellite is always above us? Why doesn't it fall down? Well, it is falling down, okay? But they put the satellite at 20,000 miles up, all right? Because by the time it gets up, as it goes around the Earth, it takes it 24 hours to orbit the Earth, okay? And as it's orbiting the Earth in that 24 hours, guess what the Earth's doing? It's spinning. How long does it take it to spin completely one time? 24 hours. So the telecommunication satellite, okay, the dish satellite or direct TV is what we call geosynchronized. It's synchronized with the Earth. Okay, so its time per orbit is exactly 24 hours. But they have to move it up, okay, with a rocket, and it's expensive, okay, a couple of $200 million, I guess, to set it up by the time they get everything done. They move it up, and it's got all the electronics on it. It has solar panels, so it gets its electricity from the sunlight, and so they have to tweak it so the orbit stays. That orbit has to be circular; it can't be elliptical. So it always stays at the same point. All right. So geosynchronized. So the further you get away. Now, what if we get as far away as 250,000 miles, which is the distance from the Earth to the Moon? The average distance. Sometimes it's closer. Right now, okay, in the last month or two, it's closest, so that's why we saw a bigger super moon. But it averages about 250,000 miles. So gravity is getting fairly weak out there, right? So, but he came up with an equation that said this. All right. I'm going to make an Earth. I'm going to make a moon. Okay? And the moon goes counterclockwise. So the moon's going with a velocity this way. And the Earth's gravity is pulling on it. Okay, so it doesn't go straight. As it's falling, okay, it drops. But as it's got just the right speed, so as it keeps going, okay, it drops again. It keeps dropping, all right, and never gets to the Earth. The same thing with our satellites. When they're in orbit, okay, the Earth pulls on them and they're dropping, but they're going 17,000, almost 18,000 miles an hour. So as they go sideways at 18,000 miles an hour, the amount of drop they do is exactly equal to the change in height. Isaac Newton figured that out. Here's what he did. Okay, I'll come back to this in a second. If this is the Earth, I'll make it bigger. All right? And if you're traveling, this is the center. If you're traveling this way, okay, let's say you're a beam of light, so gravity doesn't affect you too much. All right? Any object or anything that's on the Earth, okay, drops at an acceleration of 32 feet per second every second. Okay, what does that mean? It means that if you climb a tall building 32 feet high and you jump off, okay, 1 second later you're going to be going 32 feet per second. So you speed up from 0 to 32 in 1 second. So it's just like if you're driving your car, and you know, they say, well, you can go from 0 to 60 in 2 seconds. Okay, let's say you're driving a Tesla. And I'm not quite that fast, I don't think. What is it, 5 seconds, 6 seconds?
It's about 3.
3 seconds, oh, even better. Okay. My Subaru does it in 3.5. No, I don't know. So acceleration means how fast your speed is changing. Now it could be a negative acceleration, like when you put on the brakes and you're going 60 miles an hour, put on the brakes and you come to a stop, okay, in let's say 12 seconds. Okay, so it takes you 12 seconds to go from 60 to 0. That means you're losing what? 5 feet per second, okay, or 5 miles per hour per second. So your acceleration could be positive or negative, depending on whether you're speeding up or slowing down. There's another kind of acceleration which people forget about, okay? If you're driving in a car, okay, and you're drinking your Coke, all right, and you put it on the dash, right? Okay, I'm sure it'd be something different, maybe more like what Joanne's got there. Put that on the dash or on the hook. And you see a deer, so you turn the steering wheel, so your car's going this way and all of a sudden it goes that way. What does the bottle want to do? Does the bottle want to go with you? No, its inertia says go straight. Okay, but the car that it's in is going that way. So it looks like the bottle is going to the outside of the car, when in reality it's just going straight. Okay? So we call that a centrifugal force, a force towards the outside. All right? You all feel that, right? If your wife is driving and you're having a little nap there, and then she turns quickly and you feel like you're being pulled towards the door. You ever felt that before? Okay. So with me, it's when she's sleeping and I'm driving, okay? Because she never sleeps. She doesn't trust my driving at all. So, so there's three ways you can accelerate. You can accelerate by speeding up. You can accelerate by slowing down. You can accelerate by changing direction. Why is that? Why is that still called an acceleration? Because inertia doesn't want you to go that way. Inertia wants you to go straight. Okay? That's something nobody still understands. Einstein tried to figure it out. Why does a mass, when it's moving, wants to keep going straight? Okay? So nobody understands. It's just a property of matter. All right? As far as we know. Somebody will come along sometime and explain why matter has that property. So to change direction, there's got to be a force sideways. Think about it. You're driving in winter and there's ice on the roads and you turn your wheels. The wheels are turning this way, but your car's still going straight, isn't it? Because the wheels aren't gripping the road. You don't have the sideways force anymore to turn. Okay? So this moon or object over here, I'm going to go back to your shooting. Okay, so acceleration is 32 feet per second. What Isaac Newton said, well, if I were to go sideways, okay, so that my this height here is equal to 32 feet, okay, so if I go in 1 second, if I go sideways far enough so I'm now 32 feet above the ground, okay, I'll have fall, and my gravity will make me fall, but I'll still be even with the ground because the ground curves underneath me. All right. So what did he do? He's good at math, right? He says, "Wow, okay. So in feet, they actually did it in miles. This is 6,400 miles. All right, from here to there, and all right. So if I want to have a different length in there, how far is this over here? Well, turns out it's 5 miles. Okay, if you do the geometry like Newton did back 400 years ago. So if you could go 5 miles a second that way, after 1 second you'd be 32 feet off the ground. But as you're going at 5 miles a second that way, you're also falling. Where would you be? Well, you'd still be at the ground. Okay? So if you keep going at 5 miles a second, by the way, that's 17,000 miles an hour. If you go 17,000 miles an hour, okay, as you fall, you're following the curvature of the earth, or you're going around in a circle. Okay? Does that starting to make any sense at all? So he figured that out. So then he said, okay. So he was able to measure the moon, all right, and he knew how far away the moon was, 250,000 miles. He knew how far it went, let's say, in a day, okay, and that if it was really the Earth that was pulling on it, how far it would be. So he figured out that every day the moon comes in so many feet, or so many inches, and then he had to come out with, if the force of gravity, if the acceleration down here is 32 feet per second, what is the acceleration going to be up there? Be a lot less, all right? So in order to get that acceleration to work, he had to come up with the following thing. And this is the mass of the Earth. This is the mass of the moon. All right? So if you multiply those two masses, by then they had a pretty good idea what the mass of the Earth was and the mass of the moon. And you divide by the distance, okay, you're going to equal the amount of force you have. And if you divide out, okay, in both of the acceleration of the moon is equal to, how'd it go? Oh, we have to square this, all right? So, yes, the product of the masses, that's right. Earth and moon. And then there's a constant of gravitation here. All right? So this is the way he came up with the law of gravitation between the Earth and the moon. And then he also went along and made a big, big step. He said, doesn't have to be the Earth and the Moon. What if it's the Earth and Ben, or Earth and Alan? Okay, what would the force be? And when he did that, he found out that it turned out to be the correct force. Now, what does that tell him? What did that tell him? It told him that the Moon is an object that behaves a lot like objects on the Earth. So is the Moon special stuff? Or is it just, he came to the conclusion that all matter, wherever it is equal. Okay? So no more quintessence, guys. Everything is made the same stuff. All right? So it means that even the sun, the godly sun, is made of ordinary matter. Nobody believed him. So a whole bunch of other experiments had to come along, okay, to show that, I guess, all right. But one of the most important ones was around 1800. Somebody figured out, okay, how to, remember I showed you a prism a while ago, where when light goes through it separates into different colors? They found out that if you heat chemicals, certain chemicals in a flame, you get with sodium, you get a bright yellow flame. And if you take that yellow flame and make it go through a prism, you see yellow lines. It separates not much of the other stuff, but yellow lines. Okay? So each burning substance produces its own spectrum of colors, and that's how they can identify, okay, by using spectroscopy, they call it. Take if you don't know what it is, you burn it. So you burn some of it, and the flame that comes out, you pass that through a prism, and you see what colors you get, and you can identify it. Okay, 1811. Somebody comes up with the following thing. It takes sunlight. Okay, so here's our sun. All right, and sunlight here on the Earth, and he has an object here. He makes a little hole in it, so you have a nice beam of sunlight, and you pass it through a prism, like Newton did. All right, and then you kind of study it. You enlarge it with a telescope. So what you see, okay, you see the spectrum: red, orange, yellow, green, okay, indigo, violet. But if you look carefully, if you magnify that, there are spaces where there's no color. There are little dark lines in the sun spectrum. Okay, he was the first one to notice that, 1811. So, in other words, if we had the full spectrum here, okay, you would see from red to violet, red all the way to violet. Okay, there's some colors missing. Okay, so that was known as the solar, okay, dark line spectrum. Okay, big deal. How come though? Nobody knew. All right. A few years later, okay, somebody tries passing light through. Okay, so somebody's got a, I'm going to say sodium. Okay, he's burning some sodium, so you have a flame. Okay, and as it comes out, all right, it gives out a lot of. This is red, and this is violet. There's a lot of yellow in between here. Okay. But after he turns off the flame, okay, there's still some sodium gas left, right? And what he notices, okay, is if he put a regular light, like by then they had, they were able to produce strong white light. What they call white light has all the spectrum. If they pass white light through sodium gas, all right, you got, now the sodium isn't hot anymore, it's cool gas. You got all the colors coming through, okay, but there's missing colors. The yellow lines that, when the gas is hot, gives off bright yellow, but when the gas is cool, when ordinary light goes through it, the yellow is absorbed, okay, and doesn't come out. All right, so they said, so this is known as the dark line or cool gas spectrum. So the next thing was, could that be used to explain the dark lines? So somebody said, oh, let's look at the let's look on the sun spectrum, okay? And sure enough, in the yellow, there were two dark lines here that matched the dark lines, the bright lines for sodium. So that means that on the outer part of the sun, you know, the sun has a big ball of fire about 1 million miles wide, so it's a pretty big ball, okay? The temperature is 6,000 degrees at the surface. As you go up, because the gases that have the most energy go up, and it goes up to like 10,000 degrees. And way up there, the temperature is 1 million degrees because the real fast molecules are the ones that can get that far away. So the temperature increases as it goes up. But for the most part, it's a gas. So as the surface of the sun produces white light, or all the colors, that sunlight, as it goes through these cooler gases up in the atmosphere, the cooler gases absorb their characteristic colors. So on the sun's dark line spectrum, they identified the lines for sodium, hydrogen, nitrogen, oxygen, helium, okay, iron, uranium, no, all the elements that we have on the Earth, which we had by then we had figured out what their spectrums were. Their spectral lines matched some of the lines on the sun. Pretty amazing. What does that tell you about the sun? Is it special stuff, or is it made of the same stuff as on the Earth? Made of the same stuff on the Earth. But we had to wait a long time for that to come in as a direct proof. The interesting thing here is that after they did that, there were some dark lines extra that didn't match any of the elements that we had on the Earth. So they said, well, those are got to be the lines for an element that's only found on the sun. So what do they call that new element they discovered? What's the Greek name for sun? Helios. So what's the element?
Helium.
Helium. Helium was discovered on the sun before it was discovered on the Earth. We had to, after this was discovered, we had to wait another 10 years before it was discovered on the Earth. It was discovered in Oklahoma. Why Oklahoma? Well, there's a university in Oklahoma, okay? And there's also a lot of natural gas, in case you haven't heard, okay? So one professor just in 1870-something, 78 or 79, took the natural gas and he tried to identify what was in there by using the spectrums. And sure enough, all of a sudden, oh, there's helium in here, okay? Which he was aware of these studies, being a good physics professor and all that. So he discovered that helium was found in natural gas. All right? And so then it became, how do we separate that? Well, they used special chemical processes to separate the helium from the rest of the gas, and they found it had all kinds of special properties. All right? So there's worry that we're using helium quite a bit now. They use it to manufacture a bunch of things. We use it for birthdays. We use it for balloons, for blimps and that type of thing. That we're going to run out. When the natural gas resources go out, we're going to lose them. Not true. Because the Earth keeps making helium. Because helium, okay, is the second element. And it is atomic element 2, which means it has how many protons? How many protons? And the first element has only one proton. Which one is that? Hydrogen. Okay. So helium has 2 protons, positive, and this is in the nucleus, and 2 neutrons. Okay. So atomic mass is based on how many big particles, so that has, it's called helium-4, okay, because there's 4 particles. Its element number is 2, all right. Oxygen, for example, is number 8, atomic number 8. And is it 8 or no, 16, excuse me. It's 16, but its atomic mass is 32, okay, because there's 16 protons and 16 neutrons. So the total mass is 32, all right? So this is produced, okay, helium nuclei is also known as alpha particles, okay? And uranium, which there's still a lot left on the Earth, by the way. The Earth is about 4.3 billion years old. And the amount of uranium that was deposited with us has been decaying slowly. And when uranium decomposes, okay, it gives off an alpha particle. And an alpha particle is simply the nucleus of a helium atom. And as this alpha particle comes flying out, it changes the uranium to another element. All right, and does this at a slow rate. So we have a lot of uranium left around us. So our Earth is continuously giving us helium. And that, by the way, that's one of the reasons why the core of the Earth is a lot hotter than the outside, because the uranium in the core and throughout the whole Earth, as every time it decomposes, it also gives off heat, gives off energy. All right, so and our core is quite hot, several million degrees hot. Right? But it's solid. You say, well, how can something be that hot and not change to a liquid? Well, the core of the Earth, okay, like the core of an apple, the outer part is liquid, but at the deeper you get and all this stuff above you pushes down, the pressure is so great that even though the molecules are vibrating like crazy, they still can't separate from each other, so they become liquid. They stay liquid. And then they, at the core, they actually become a solid. So our core is solid, okay? A lot of uranium down there, a lot of iron. And the outer core is liquid. Then after that, we'll go back to solid. The mantle of the Earth is solid, okay? Made up of different kinds of rock. Okay, so it's through, and this is where physics started becoming called astrophysics, where we use physical things that we've discovered about things on the Earth that apply to the stars as well. Okay, so it's around the 1850s, 1860s is when the term astrophysics came into play. Okay, so, but anyway, so the Earth no longer the center, okay? It's made of the same stuff as the planets and the sun and the stars, and so everything, all matter is created equal, all right? So, and Isaac Newton wrote that up around the 1860, well, maybe a little longer, around 1880, all right? He was in his 40s. So, and then philosophers, thinkers, like especially there's one in France, John Locke. I don't know if you've heard of him. He was one of Thomas Jefferson's mentors. And he picked up on the idea that, well, if all matter is created equal, no special stuff, why can't all men be created equal? And that's where Jefferson got the idea, and he put it in the Constitution. It is self-evident that all men are created equal. Okay? And today we know that what he meant by men was all humans. So it includes the ladies too. So but that had if it affected Thomas Jefferson, okay, around when Jefferson was a student and learning all that stuff in France, then he wrote it in the Constitution. And the other thing that Isaac Newton found was that for every force, if I push on the bottle, okay, it actually pushes back on me. if I try to push harder, okay, it can only push back. If it can't push back harder, I can't create a greater force, then it pushes back on me. So I'm going to lean on the wall, on the air. Okay, the air doesn't have much inertia, does it? But if I lean on here, okay, if I push there with 50 pounds, it pushes back 50 pounds. So the two forces, all right. If I try to push a little harder, if I push hard enough so that the wall starts moving, all right, call 911 if you notice. If the wall starts moving, you say, well, you're pushing harder than the wall. Not true. Yes, you're pushing harder, but then the wall's inertia, or whatever is holding it in place, isn't strong enough to push back on me. So as soon as it starts moving, my force automatically decreases a little bit, okay? So that forces always are equal and opposite whenever you have an interaction. You can't have a force all by itself. So every time a force is generated, there has to be an equal and opposite force. All right. So that idea from Isaac Newton went into creating the balances in our Constitution. Okay, we have three branches of government, and they're all equal, and the one isn't stronger than the other. Not supposed, according to the great thinkers of 200 years ago. They're supposed to be all equal, balance off. All right. Isaac Newton came along. He had to stay home. While he was home for a couple of years, idling around, he figured this out. He was 20, 21 years old. Finally, after the Black Death subsides, he goes back to the university, and his math teacher, okay, that taught him when he was an undergraduate, listens to him explain how he came up with a way of calculating how those forces, that equation came around. And he was able to figure out why the planets, okay, have an ellipse. Because as you move away, okay, in the ellipse, the force of gravity weakens, so you slow down. Okay? And you slow down, so you change direction now. As you start coming in, you're starting getting closer. And so your force, so you speed up, and then you speed up enough so that you kind of make around the corner. Okay? And the flatter the ellipse is, the bigger the difference in speeds from when you're close, going quite fast, and then far away. And that's, the comets have very long orbits. So they come in from the Oort cloud, they come in and they pick up speed, and they just, if they're not just the right distance, they'll crash into the sun or they'll go by completely and never come back. So it's got to be, not all objects that come from the Oort cloud end up being comets. They all made the same stuff, but they don't go back on the, okay. And as they're coming in, by the way, the comet is a dirty snowball. I think somebody said that last week. It's a mixture of ice, okay, dirt, what else is on there? Frozen carbon dioxide, okay. And as it's coming in, all right, the side that's facing the sun gets hot and starts boiling off. And as it boils off, the solar wind, the little particles from the sun that create the northern lights, the solar wind comes in and pushes those particles back, and then as the more of that, then that part starts looking like a tail, but it's really a lot of, okay, we look at it from thousands of miles away, so it looks like a tail, but it's really just loose gases coming off from the comet. And as it goes around the sun, okay, the tail always points away from the sun. And when it's returning, it's going back, okay, the tail's in front of it because it's escaping from the sun's gravity, but the solar wind is pushing the tail up ahead of it. All right, so interesting to look at orbits of planets, of comets. Okay, so I promised you an experiment. We'll do it right now, okay? So I got some very expensive equipment, all right? So you'll say, what the heck is that? Have you heard of thermodynamics? Thermo means heat, right? Dynamic means forces and motion. Back in 1732, okay, there's a gentleman in Scotland again, just like I told you last week. There was a beer maker by the name of James Jules. I forgot the name last week, but his name was James Jules, that was making beer, and he noticed in his little lab that he could make water get warmer by making a paddle churn through the water. And he actually recorded how much heat was created from this paddle turning. But anyway, before him in 1700, a guy by the name of James Watt. Does that ring a bell? You know what a unit of power is? Okay, watt or thousands of kilowatts, named after him. James Watt was a young student, also from the University of Glasgow, that was hired by a coal miner, a guy that owned a coal mine. Okay, and this guy was kind of ingenious. His name was Newcomen. Okay, Robert Newcomen. And by 1732, the Black Death that Newton was in 1660 or something like that had killed a lot of people in London. But like after a catastrophe like that, like after World War II, there's a baby boom. Okay, so the human race kind of adjusts, right? So a lot of babies grew in the London area, and what were they using for heat and construction? Wood. Okay, so all imagine a circle getting bigger and bigger. All the woods around London were being cut for heating or for building. Okay, because of this baby boom. And I'm a baby boomer. Any other baby boomers here? Okay, a few of us. You're too young. So they had to resort for something else. What is it they were resorting to? Something you dig out of the ground that's black and sooty? Coal. Okay, so coal mines, and a lot of the first coal mines, the coal was right on the surface. Okay, but then the dike got depleted. So by the 17-somethings, they had to dig a hole, dig down. And when you dig a hole, you'll hit something pretty soon, right? It's kind of wet, okay? You're going to hit water. So how do you go down in a mine that's full of water? Well, you have to pump it out, okay? So what do? The engineers figure out that you could have a horse, okay, going around a turnstile, turning a crank, and that crank would operate a pump that would pump the water out of the mine. But horses are kind of messy, okay? If you have a horse, if you're down in a hole and there's a horse making circles around you, and that horse eats hay and then produces something else, and it rains, where does the rainwater go? It goes down the shaft, and what does it carry along with it? Okay, so being a coal miner back then was the dirtiest, smelliest, worst job in all of England. And so he had a hard time finding people that were willing to, he paid well because the coal sold well, but he had a hard time. So he said, I wonder if I could come up with a substitute. Instead of using a horse to run this pump, what if I could find a substitute for it? And then in the village, they had a water tower made out of big beams that were tied together in a big ring of iron to a water tank. Okay, so an idea came to his head. Okay, so this tank was sealed at the bottom, open at the top. So what if I put something in there that's going to be almost the same size as the tank? Okay, so he made a wooden piston so that would fit in there. And so that thing, and he put felt or something around the edge to kind of seal it, so that it dropped in the tank. And right above the bottom a little bit, he had a pipe coming out that was connected to a big boiler. So he used some of his coal to heat up some water, and the water turned to steam, went in between that piston that he'd created in that big tank. And as the steam went in there, it pushed the piston up. Okay? And then that piston was attached to a lever, a cantilever, that one end of it went right over the mine. Okay? So when the piston went up, the lever went down. Then he'd turn off the steam and open up some coal and shot some cold water in that space. So the steam condensed, but the air pressure on the outside was enough to push the piston back down. And when the piston came down, it pulled up the other one, which ran the pump. Okay, so he invented the steam engine. Everybody thinks James Watt invented the steam engine. It was Robert Newcomen. Okay, but it was very slow. It took like a half an hour for a cycle. Okay, so he hired this young engineer from Glasgow, the University of Glasgow, by the name of James Watt, to see if he could improve the engine. So James says, "Oh, you know what?" He says, "Every time you shoot cold water to condense the steam so that the air pressure can push it down, it cools the holes. Why don't we make a little side chamber here, okay? Or we'll shoot cold water in the side chamber, okay, so the steam can condense here and not cool down the whole thing." Well, he doubled the speed of that engine. So instead of a half an hour, it only took 15 minutes for one cycle. Okay? Then here's the other thing. He says, well, we're letting air pressure push the piston down. What if we ran steam on top to push the piston down? Which means you have to have a valve that switches the steam from under the piston to over the piston. That was kind of clumsy. So he took the whole thing and turned it on its side. So the piston was going back and forth this way instead of up and down. And then he had a chamber on top with a sliding valve. Okay, as the steam came into one side, it pushed the piston that way, and when it had gone, there was a little wheel there that switched the valve over, so the valve went, closed that hole and opened the hole in the other one. So now the steam switched over to the other side of the piston that pushed it back, and then the valve switched again. So it was a double acting steam engine. Okay, 50 times faster. And it didn't have to be the size of a room. He could make these engines about this big. Okay, the first steam engine was not very big, and it was able to replace. Well, he didn't know how much it could replace, so he tried to compare it to a horse. Okay, and then he, at the size, he says, "Well, this will do the work of 2 horses." So it's got a power of 2 horsepower. Okay, and that's why in the British system we use horsepower for our units of power, and in the metric system, okay, we use watts. All right. So but nobody wanted to buy those darn engines. Okay. So he said, "They're free. We're making them. If you want a steam engine, come and get it. It's yours." What was his boss in the business of doing? Selling coal. What do you need to run a steam engine? Coal. Okay? They were giving away steam engines, okay, so that people would adapt them to, let's say, replace a waterfall or something to turn a mill, or eventually it was made to replace horses to pull, so they became, not horses, but sails on a steamboat, so the first power. Okay, it went up the Hudson River here. Paddle boats, and then trains, and by the 1820s we got trains. And his boss became a multimillionaire. Okay, well, back in those days he was making like $10,000, which is the same amount of money today as being a billionaire probably. But so anyway, that's the transition. Okay, to some of the things that I want to show you over here. So steam engine is what I wanted to talk to you about. Okay, this is not a steam engine, but if you understand how a steam engine works, you understand this can be used to make snow or clouds. Okay, what am I doing? Pressure, high pressure, low pressure, right? Okay, so let me make you a diagram of how a steam engine is going to work. Well, maybe let's do the experiment, then I'll explain how it works. Okay, so we have enough. I have enough here to do 4 groups. If I can find the other one, is there 4 bottles? Oh, I threw one away. All right. So let me tell you something about when you're squeezing the bottle, you're pushing into it. Guess what happens to the air molecules in there if you push into it? They start moving faster. If they're moving faster, what's that called? They heat up, okay? And when you let go, okay, so whenever you compress a gas, it gets hotter, all right? But you have to do work to do that. It doesn't, the heat doesn't, and that's one of the things that James Joule had found out. There's a connection between heat and mechanical So mechanical, heat. All right. You let go. Now the bottle's doing work on me because it expands back. So it's doing work on me. So what happens to the temperature when you let it go? Drops down. So expanding gases get cooler. All right. So have you heard of something called dew point?
Yeah.
The dew point is when the water vapor in the air, okay, the temperature of the air is the same thing as the temperature where this water vapor condenses. So, for example, in the summer, if you go in your cellar, you see all the water pipes, the cold water pipes are all covered with water. Well, it's not that the pipe is leaking. The water's coming from the air because the temperature around the pipe is cooler than the air temperature. And when the air molecules get there, they slow down, cool down, and they can't hold on to their water molecules as much, so they come back as liquid water. All right. So I already put some liquid in here. Now I have to put something else. Okay. Dawn, close your eyes. There we go. What's that? Okay. Let's see. I'm going to try and see if I can. Did I open one up? No, not yet. And you'll say, well, why do I have to do this? Well, I'll explain that later. Okay, so I'm going to compress this, okay? What's going to happen to the temperature of the air when I compress it? It's going to go up. So does that raise the dew point or lower it? It raises it. Okay. Oops. Did you see that? What does that look like to you? Okay, let's get 4 teams. You have to push real hard and let it go real quick. Gets better with time, right? You want to have a group? Get 2 or 3 people. Take turns. See, it's called a cloud maker. And it follows the first law of thermodynamics. Rosie, you want to be the cloud maker?
Rosie, I haven't heard that.
Make sure you let your buddies. Why does a cloud appear? What has to happen to the temperature of the air for the cloud to appear? Linda. Go ahead. Has everybody made it?
I'll try it.
Lester hasn't made a cloud. You got to make a cloud, Lester.
Watch several demonstrations. I believe it. That is so cool.
We feel it warm.
You got the magic touch, Joe.
So
So what's going on in there? Why is this? It's not just a fun experiment, but we can do it at our age. I do it with 6th graders, and they say, "Why, Mister? Why is it doing that?" And so, but basically, it's a pretty world almighty law. It's called the first law of thermodynamics. Okay, so, and it ties in. Nobody could explain why the steam engine works so good. Okay, you needed to have heat, right? You put heat to heat up the water. It expands, and as it expands, it pushes things, right? So that's mechanical work. Okay. So, a gentleman, a philosopher, a scientist by the name of Sadi Carnot came up with this expression. Oh, I forgot my Where's my eraser now?
Over here.
Right here, you're.
Oh, good eye, thank you. Okay, so we're gonna make, I hope, this is gonna be a little abstract, but we're gonna represent the heat source as just an object. Oh. So let's say I make this like your boiler, right? So you got heat coming in here. So heat source. So, and in a steam engine, the heat source is the boiler where you put coal in, it burns, heats up the water, and then the water goes to a chamber, okay, with a piston and makes the piston go back and forth. And of course you have to have the valves and so forth. Now, is a gasoline engine, what's the heat source in a gas? There's no external boiler there. Why is it called an internal combustion engine? Because the heating takes place inside the engine itself, right? The gas burns in the cylinder, not in the boiler sideways. But it's the same idea. The gas and the air are mixed, brought in, it's proper, lights it up, and the chemistry, the chemical reaction, the gas explodes. And what does exploding gas do? Well, it can blow up a building. Well, here it's strapped in this metal thing, so it pushes on a piston, which is connected to a crankshaft that makes the wheels of your car turn. Okay? So it goes from heat to mechanical work. All right? So here's your heat source, whatever it is. All right? And it goes to an engine, a heat engine. All right? So the heat flows down here. Now, very important that this engine has to have an exhaust, right? Because if there's no exhaust, there's no place for the more gas to come in or more fuel to come in. And the exhaust, when it comes out, okay, it goes to the environment. All right? So this is waste heat. But the engine puts out a certain amount of work, doesn't it? So some work is done, mechanical work. All right, so this is just a diagram here. There's no, I'm not trying to copy the actual parts of an engine or a system. Okay, so heat tends, this is second law of thermodynamics, is heat always goes from hot to hotter or colder, hot to cold. And there's a reason for that too. It deals with entropy, which I'm not going to go into entropy. All right, but it simply means that, let's say you have something hot where, according to the latest theory, is that a hot object, the molecules in there are vibrating very fast. You put it next to something that's cold, okay, the fast-moving molecules will bump into the slower ones and make them speed up. So the cold gets warmer, but what happens to the hot one? It gets cooler. Eventually, they get to be the same temperature. So in that respect, the second law says that heat always travels from high energy or hot to cold, to lower energy. All right? So if there's no, let's say this heat source and the exhaust is the same temperature. Will it want to go from here to there? No. So you've got to be able to dump your extra heat, or the heat, it's got to be able to expand into something, right? So heat source goes through an engine, you get some mechanical work out of it, all right? So the amount of work you get, the work you get from an engine, okay, is equal to how much heat you put in, heat in, minus what? The heat out. Right? So how come a gasoline engine at the most is about 16 or 17% efficient? All right? Because if you mix gas and air and put it inside of a piston, okay, then the valve's closed, so this is now sealed above the piston, and the spark makes this explode, okay. If when you mix them, the temperature is high enough so that the gas explodes before the piston starts coming back down, you get a backfire. All right, doesn't work well. All right, so it can't be too hot from the compression. On the other hand, and so the amount of wasted heat that comes out of the exhaust, the hotter the exhaust, the less efficient your car is. Okay. Now, if you switch from a gasoline type of engine, four-stroke engine, to a diesel engine, diesels don't have spark plugs. You know why? Because they don't mix the air and the diesel fuel outside. What they do, okay, the intake of a diesel engine is just air. Okay, so the piston comes down, sucks in some nice fresh air, okay, valves close, then the piston, after it's gone down, comes back up. And what does it do to the air? Okay, what happened to the air here when you squished it? Okay, the air gets hot. There's a compression ratio of 12 to 1. Okay, so if it's 1 atmosphere, it goes to 12 atmosphere. In that place, the air gets extremely hot. Then there's a little nozzle on top of the engine that squirts a little spray of diesel fuel. Hits that hot air and then it explodes. So the fuel and the air are not mixed ahead of time. They're actually only mixed inside. And because you can get much higher compression, see in a gas engine, if they are already mixed and as you compress, okay, it'll get hot enough for the gas to explode ahead of time, so the piston hasn't come all the way up and okay, can't make the turn back down to explode ahead of time, you get a backfire. So you have to limit the amount of compression you put in. Diesel is, well, the only limit is how strong your engine is. Okay, so if it's a 12 to 1 ratio, all right, temperature goes up so high, you don't have to burn petroleum. You can burn grease from your French fry cooker. Anything, okay, that you can spray in as long as you thin it out enough. Okay, and they do that. They take leftover French fry, they filter out all the dead potatoes in there and they just keep the oil, okay, and they mix that in. Matter of fact, maybe 20, 30 years from now, when you fly down to Florida for the winter, okay, you'll be powered not by petroleum fuel, you'll be powered by vegetable fuel, okay? Because turbines aren't like they don't have pistons, but they work the same way, okay? The air is brought in, there's a bunch of propeller in it, okay, that suck in air in the front of the jet engine, compresses it enough so it's quite warm, then you inject the fuel, the little nozzles are behind here, that explodes, but the entrance is smaller than the exit, so most of the power goes out back. There's another set of small propellers there that turn the big propellers up front, but the exploding gases going out that way create a big push that sends the plane forward.
So, using your analogy here, where's the push coming out as waste?
It comes out as work, yeah.
As
Because-
work?
Yeah, because work always involves force pushing something. Okay, watch. See how much work I'm doing? Oh. Did I do any work? I pushed hard. Nothing moved. No work. I'm getting tired because my muscles are actually moving. By the way, you get these little microscopic fibers that are moving back as you push. But the object, I'm doing work internally. I'm going to get hot. But I don't do an external work. But anytime you have a reaction of some kind that pushes something and it moves, you get work. And that's measured. The unit for work in the metric system is named after the guy who came up with the conservation of energy, James Joule, the beer guy, the beer maker. You heard of Joule's beer, right? Still going on. I'm just made that up. Okay. So, can you imagine this here? So, efficiency, okay? Efficiency of an engine depends on any efficiency of any engine or machine is how much work you get out, compared to the work you put in. Okay, if you get out as much work as you put in, that's 1 to 1. How much efficiency is that? 100. Okay, but let's say you get out only half as much as you put in because, let's say you've got a simple machine where you have a jack that lifts up a house or a car. Okay, you can figure out the work. You push with a small force a long distance many times. The house goes up this much with a big force. Same amount of work to lift up a house as, okay, big force, small distance. It's the same amount of work as small force, long distance. That's the secret of a machine, why we use them. Okay, it multiplies our force. But in the process, there could be friction and heat in there. So when it comes out, if you get out less work than you actually put in, let's say you only get half as much work, then it would be 50% efficient. In a gasoline engine, internal combustion, the best gasoline engines get 15-16%. Okay? And that's because the exhaust that comes out is quite hot compared to the temperature inside. A diesel engine, the internal temperature is because of they can compress it much more, so it gets quite hot. And when they inject the fuel, okay, that burns at a much higher temperature than the exhaust. Okay, so the difference. So best diesels are around 60%. Okay, that's a lot more than, all right. So the only thing is, though, you have to keep. Where does that waste heat go? Well, here on the Earth, okay, we're like an island in space. It goes back out to outer space. And that brings up a topic that I was hoping to get into with these lectures, something known as relativity. Okay, so relativity deals with how things compare one to the other relative to each other.
Another class.
We could do that. Dr. Raymond over there. But just keep in mind that our universe that we live in, this wonderful place we live in, and this great ball of stuff that by some miracle it's just balanced. I keep thinking of the poor astronauts that are going to end up having to go to Mars, right? They're going to have an environment similar to what we have here in order to stay alive. How do you miniaturize the Earth and make it so that it can move, okay, for almost a year, all the way up to Mars, millions of miles away. Okay, and then when they land and do experiments and stuff, then they want to come back, unless they're like the old pioneers. Once they went out west, they stayed there. Okay, that's probably going to be. Yeah.
What are they doing about the radiation when they travel to Mars? Has anybody come up with shielding? Or?
Have you heard of mushrooms?
Yes.
Okay, they absorb radiation very well.
Really?
Yeah, you're going to make a like a 6 or 8 inch cocoon of mushrooms. That's the latest I've heard.
Thank you.
Darn good question. Yeah.
Seriously? Oh, yeah.
Well, the most dangerous ones are the little particles, the electrons and protons. Okay, gamma rays are dangerous too, but if you can absorb at least the solid radiation, because radiation, electrons are really particles, they're not waves, and if you can at least absorb the solid part, these are the ones that carry the most energy. So they'll have like a mattress made out of mushrooms around where the living quarters. So, yeah, good point. Okay, any other questions? Oh, Lester.
Does one mushroom work better than the next?
Work better than what?
Than the next?
Well,
Does Aconitum muscaria work better than Saccharomyces cerevisiae?
yeah. The other thing is, too, you could use the people that work for the Navy that are assigned to nuclear submarines. They live not too far away, like from Dave to me, from the nuclear reactor. Okay, what keeps that radiation from getting to them so they don't get radiation sickness? Well, there they use lead. But lead is heavy. It's costly to put it into orbit. Why don't you just bring some seeds, okay, and some water, and then let those grow, and then you can build your shelter as you're going out. You also have to grow your own food, you're gonna have to recycle all your waste, okay? When you go to the bathroom, it's not gonna go into space, it's gonna go back into, okay, be ready to go back in somewhere, sometime somewhere else. All right, and there's I was reading, was it Arizona, a town, I
Didn't they
think,
try that years ago to buy us?
they did,
Tried that.
yeah. Well, it was a
It was like
beginning.
week or something.
They collect a lot of data from that. There is a town, I think it's Arizona, okay, which is quite dry, and yet they have waterfalls, they have wading pools and stuff like that. Where do they get their water? They get it from the septic system.
Yeah.
They reprocess their wastewater, okay? And there's one in California, somewhere, I forget the name of the valley, where they're actually, after the water gets purified or clean and separated, they actually pump it into the ground. And there, it goes into the natural water table. Okay, so people, wherever their houses are, they can just dig a well and get this water, which maybe a couple months before, they had just rejected down their toilet. But as it travels through the ground, okay, it gets cleaned
It
or
must cost a lot.
but it's already pretty clean when it comes out of the waste sewage system. Reprocessing is already pretty clean. Did you see the mayor of Paris? She went down to the Seine River and took a glass, took a nice big drink. That's how the politicians have to do it. They have to convince the people this is safe water. I wouldn't do that. Okay, I've actually done it. We went to a place in Massachusetts where they had University of Massachusetts had a sample retreatment plant, and the professor, okay, took a glass, opened up, and we saw the stuff going in. It wasn't very pretty. Okay, and he went around through, and it came out. This was the exit. And he opened the valve, took a drink. Anybody else? I said, I'll do it. I had a drink. I'm still alive. Okay, so a lot of it is up here, isn't it? But think about it, right? The molecules that are inside of me now. Guess who had these molecules 68 million years ago? Some dinosaur roaming around. Nature keeps recycling itself. Okay? So, well, no more questions, or I'll be glad to have questions.
Thank you very much.
With a quick answer, I hope.
Oh, okay.
Why does the exhaust from a diesel engine smell so different from the exhaust from a gasoline engine?
Okay. Well, it's the fuel that they use. They use cheap fuel. That's why they're less expensive to run, plus they're more efficient. Okay? So, in a gasoline engine, in order to avoid the early combustion during the compression state, it has to be pretty clean stuff. Okay? Whereas the diesel engine, anything can be used as long as it doesn't plug up the valves. Okay? And so they send everything through. Not all of it burns, unfortunately. So the particles that come out, those are the ones that are dangerous to our health.
Yeah.
I mean, there's some particles that don't quite all burn.
Thank you very much.
Thank you very much, Ben. This was scintillating.
I'm bad. One of these times you guys invite me, I'll try to stay on schedule.
I
What is there?